All right, sorry for the delay. I think we're ready to go. So yeah, apologies about Tuesday. So basically, yeah, class was canceled on Tuesday, but we wanted to stay on the syllabus, and so Mark recorded a video and put up a video lecture of the DLM stuff that he was going to cover on Tuesday. And I think if you haven't gotten a chance to look at it, that's totally fine. We'll just we'll go through that in the lab, and I think the examples are pretty straightforward, and Eli and I will kind of help you with that. And I think looking at the snow forecast, it looks like there's more snow coming this weekend, which is terrifying to me because it means that if my son's school's closed, then I don't go to work, and instead we are cooped up at home. And so I think I'm gonna try to get Tuesday's lecture also posted to the web this weekend, just in case we have the same thing happen again, because I think that's definitely in the realm of possibility. And so I think we'll do that Tuesday. Eli and Mark, and I think a couple of you are gone next week in San Diego, and so next week we'll kind of talk some more about the Bayesian stuff that I'm talking about today, and then we'll talk about some hidden Markov models, and Eli and Mark will be back the week after. So today I'm going to be I'll try to spend like an hour or so talking about kind of an introduction to Bayesian time series modeling, and then we'll do the DLM lab, and then I think we'll try to wrap up a little bit early, so probably 3:30 or so. All right, so let's see here. It's not working. So has anybody never fit a Bayesian model before? Has anybody used Bayesian methods before? A couple of you? Most of you? Trying. Good. That's kind of what we were hoping for. I think for most of the material that we'll be talking about the next couple of weeks, we'll be relying on this software or program called Stan, and Stan is kind of a language that we can call from R. So today I'll kind of give a quick overview of what Stan actually is. We'll talk about manipulating and plotting some Stan output using some pretty simple functions, and then kind of thinking about applications to some time series models, all of just kind of the flavors of models that we've talked about in this class, the univariate and multivariate models. So this is just kind of a review of the kind of models we've talked about so far. We really started talking about kind of how ARMA models differ from regression, and then moving on to state space models, where we have a process model that represents kind of our latent or unseen state of nature, and then we layer an observation or data model on top of it. Dynamic factor analysis is something that Mark just talked about last week, I think, where we have we have a multivariate stream of data, multiple time series, and we want to use some dimension reduction tool to identify kind of synchrony or some kind of latent number of shared or some number of latent trends that kind of can explain the data in a simpler way than fitting independent models to each of those. Mark also talked about dynamic linear models on Tuesday. We'll follow up with that in lab today. And the DLMs are essentially a regression model where we have an intercept or a coefficient on a covariate that's time varying. And so there's a random walk in your covariate or a random walk in the intercept is the DLM. And then finally, thinking about the multivariate state space models, which are kind of, I'm referring to generically as these Mars models. These are similar in a way, the inputs are similar to a DFA, but with the Mars model, we're fitting independent or potentially correlated state space models to each of the different responses, and thinking about how we're structuring the different AR parameters or the different interactions between time series, as well as how the different process and observation errors differ between each of those. Okay, so why Bayesian? I think that Eli gave a good synopsis of this maybe in the first week of class. In that in a lot of the cases where people have time series models or these methods are being developed, people have really high frequency data that's often normally distributed, and that's often the case if you're working in things like finance or maybe medical fields where you have just a ton of data. I think in the fisheries and ecology world, we often have data that are substantially more complicated. We have data that are kind of missing in weird ways, or they're zero inflated. We have data that are often skewed and definitely not normally distributed. And so for any of these cases, the Mars approach, while it's fine for normally distributed data, it doesn't work so well when any of these assumptions get violated. So in the Bayesian world, this is actually pretty straightforward to do. We can extend kind of the same kind of basic machinery that we've learned with any of the univariate and multivariate models so far to just dealing with non-Gaussian data, for example, or making parameters shared or hierarchical with random effects, for example. We can include non-linearities, which you can't really do with Mars. And so I think that these are all advantages. I think one of my the other thing I like about the Bayesian model is that when we're fitting a Mars model and we want to generate uncertainty estimates around parameters, we often have to do this bootstrapping. And the bootstrapping is complicated because bootstrapping in Mars involves generating these new or pseudo data sets, fitting the Mars model to the data set again, saving those parameters, and repeating that process a large number of times. So if you do that 200 or 300 times, and each iteration takes 5 minutes, all of a sudden your computer is running overnight, and it gets to be kind of a pain. In a Bayesian world, though, we never have to do that. You just have to fit the model once, and when you fit the model once, you get uncertainty estimates around your parameters and uncertainty estimates around your states or your latent processes at the same time. So each model might be a little bit slower to fit compared to a maximum likelihood method, but it's giving you everything at the same time. Okay, so what is SAN? Has anybody in class ever used SAN before? No? Okay, has anybody used, what about like JAGs or bugs? Few people? Okay. So so we used to include JAGs and bugs in this class, and you can do all of these SAN models. I think all of the JAGs and bugs code to basically do the same stuff we'll talk about today is all the JAGs and bugs equivalents are still on the website. And about maybe the last iteration of this class 2 years ago, we switched from JAGs to SAN, and I think the main motivation is that the developer community behind SAN is just, it's huge and growing quickly, and the number of applications and the kinds of models that they are allowing is just rapidly expanding. And then the community, like if you have code and you have or a bug and want help to figure out a solution to something, the community is super responsive, and it's really great. So I think for that reason, and the number of people in fishery in SAFs who are using SAN is increasing too. So I think that we wanted to make the change. It's extremely powerful. It's cross-platform, and you can use multiple languages. So for this class, we'll pretty much only talk about R. But if you're using MATLAB or Julia or any of these other tools, SAN offers interfaces with those. So you can use the exact same SAN model and call it from R or any of these other programs. The other cool thing about it that we'll talk about next week is that today we'll talk about just generating estimates, these kind of posterior estimates from our models using Bayesian sampling. But we can also do maximum likelihood sampling with SAN, and so we can use optimization to get equivalent estimates as we would with Mars. Some useful links here are there's the homepage link. Will take you to the SAN homepage. The manual is something like 250 pages long and growing. It seems like it's growing exponentially every month when I check it, with just more and more models being added. And so I think that's a great resource. And to install it, you just use this RSAN package on CRAN now, and that will automatically install everything you need for it. So it makes it super simple and pretty easy to use. So the options that you can use SAN for this class is obviously you can write your own code. I think that after we kind of get the hang of it today and next week, this should be pretty straightforward to do. There's a ton of examples in the manual, a ton of examples that we'll give you for this class, and you can extend any of those pretty easily. There's a number of existing packages that I'll talk about that are, yeah.
You're not sharing.
Oh, shoot. Thanks, Eli. Do I just hit show?
Try that.
Sorry about that. Sorry about that, Newport. So yeah, options for the code are obviously write your own. 2, use an existing package. There's a couple out there that we'll talk about. or for the purpose of this class, we've also bundled a bunch of the time series models that we're all familiar with now, and that'll help you get started to fit these kinds of time series models. Let's see here.
So I noticed a number of you have used JAGs before. If you look at the univariate state space and the multivariate state space chapters, at the end, there's a chapter that shows you how to write a model, a really simple model in JAGs, and then it shows you how to do it in STAN. So as you're learning STAN, it might, if you're familiar with JAGs, that might help you to compare the two.
Yeah, and I guess next week we'll talk about a little bit on Tuesday about kind of writing our own models. And so if folks have used JAGs before, I'll try to make some comparisons between the two, going back and forth, because there are some important differences, but essentially they're trying to do similar things. So the two packages to highlight on Crayon are, there's the RSTAN package and then the the RSTAN ARM package and the BRMS package, and both of those are part of the STAN kind of developer community. They're both great because they use the same exact syntax that everybody's probably familiar with, which is kind of the basic R. So in RSTAN, for example, there's a stan_lm and a stan_glm, which are equivalents. They're basically Bayesian equivalents of LM and GLM. So those are very flexible. If you're fitting a mixed effects model with normal or non-normal responses, the stan_gleamer is essentially equivalent to something like lemur in the LME4 package. Some potential limitations here are that packages like BRMS let you include autocorrelated errors, which is great if you're fitting a time series model. They allow for non-normal data, some different smooth terms, but one of the limitations is that, for this class we're thinking about DFA models and these dynamic linear models where we have this underlying process, and the process is this autoregressive process where the value of that at time t+1 is a function of where it was at time t, and these packages don't let you fit that kind of model, unfortunately, and so that might change in the future. But for now, these AR processes on parameters like a DLM or a latent variable like a DFA aren't included, and they also don't include allow for multivariate data. So that's a big deal for some of the applications in this class. If you're fitting DFA or a Mars model, we're going to run into cases where we often have multivariate data streams. So the advantages, like I said before, so I talked about the functions in the RSTAN ARM package. These are the same functions in the BRMS package, and we have the same syntax like we would have with LM, where we have some response and there is potentially some interactions. We can include grouping variables representing random effects, in this case, random effects in the intercepts. What's cool is that if anybody's ever used a GAM before in the MGCV package, there's essentially a Bayesian equivalent of those smoothing terms with the BF function here. So the BRMS package is super powerful. Essentially, anything you want to do with GAMs or linear models, it can do too. That's just to keep in mind. If you have data or problems where you want to get Bayesian estimates for these kind of hierarchical models, this is kind of the way to do it. Okay, so to install, so those are kind of the existing packages. To install the code that we bundled for this class, you'll want to get RSTAN first, and then you can do this later, but there's the DevTools package if you don't have that already. And then we'll use the DevTools package to basically install this repo from our class website. And so this package is called ATSAR, and that should install cleanly. And once you've got STAN installed, that'll just load a bunch of like the 15 or 20 models that we put together for you. Okay, so then given that that we can get STAN installed, I guess if people try that and you have any problems, shoot me an email or message and let me know, or post an issue on GitHub. But we'll start with kind of a super simple example to illustrate how to work with the STAN output. And this is the time series of Nile River flow that we've seen before, where essentially this is mean annual flow. There's a dam that was put in, in 1900, and kind of a level change between pre and post dam where flow decreased. So for starters, what we'll do is even though if we look at the data, fitting a regression model to this data without that change point, it would probably in practice be a terrible idea. We're gonna do it anyway because it's kind of the simplest possible model we can fit. And so in this case, we're going to basically fit this Bayesian model, Bayesian regression model. And because it's regression, we could also do the same thing with RSTAN-ARM or the BRMS packages. But in this case, we'll use the code for this class, which is in this ATSA library. And we have a few basic functions in here. This first one is just fit_stan, and so that's just going to be fitting a STAN model. On Tuesday, we'll get more into the kind of the nitty-gritty of what these model files actually look like and what they do, how to tweak them to meet your to fit your exact application that you're working with. But this will involve no actual working with the STAN backend. And so in this case, we're going to pass in our response, which is kind of just our flow data, and we're going to pass in our covariates, which are x here is just going to be a vector, where we're passing in a vector of 1s because we want to estimate this intercept. And then we have to specify the model name. So in this case, the model name is just going to be a regression, and those are the only 3 arguments that we'll specify for now. So the output of this is going to be this LM intercept variable, and kind of by default, the way we've set this up is that if you've never done a Bayesian model before, this is probably new, but most of you have. So ideally, we would want to have some burn-in period for each of these. I guess we would want to start with specifying how many MCMC chains we're fitting. So ideally, we would start, pick 3 different random parameter initializations and start 3 different chains in 3 different parts of the posterior surface, and then let the model essentially explore the posterior surface, all converging to the same spot after everything's converged. So ideally, we would specify some number of MCMC chains, ideally greater than 2 or 3, and then often we have to specify this MCMC burn-in. And so in the case of if you start in a bad spot on the posterior surface and you're wandering, your parameter estimates are essentially wandering around the bad spots, you would want to discard that first X% of the MCMC chain to really focus on the part of the chain where things are actually converging. So these are not arguments in this specific call here, but that's because we've already kind of specified the defaults. So by default, this function will run 3 MCMC chains for a burn-in or warm-up of 500 iterations, followed by 500 more. And so in the case of the defaults, if you're saving 500 iterations times 3 chains, you get total estimates of 1,500 parameter samples from the posterior. Okay. So once we've got the model fit, there's a number of ways to work with kind of our basic functions in the RSTAN package to get out the parameters that we're interested in. So in this case, we'll start with the extract function in the RSTAN package, and this will take as an argument. We fit that LM intercept, which is just kind of the regression model, intercept only, and we'll pass that into the extract function, and PARS will give us a list now of the different parameters that we're estimating. In this case, we're estimating the intercept, which is called beta, and we're estimating a variance or observation error parameter called sigma. So we can do anything you want to it using kind of the basic plotting functions in base R. So this is just a histogram, for example, of PARS $beta. We could do any kind of summary to this too. You could calculate, I guess some of this is actually, I'm going to zoom out so it's not cut off. Right, so you could do any kind of summary. You could calculate the mean or calculate some quantile very easily as well, just like you would with any other object. Okay, so then thinking about plotting, I think that when we look at the class of this LM-intercept thing that we just fit, it's a stand fit object, and because it's a stand fit object, it extends all of the different attributes that that these fitted stand model objects have, and so there's a bunch of different diagnostic plots that are super useful to look at. So the first is going to be what are called these trace plots, and as I said before, if we're starting the model in 3 different parts of the parameter space, and we let it run for a large number of times, we would ideally like to see that things are converging in the sense that the parameters, every individual chain here is going to be stationary, so there's no trend with respect to the mean or the variance. We also want to see that all 3 estimates are kind of converging on the same value, and so in this case, for both our beta and our sigma, it looks like they're kind of converging or agreeing on the same value. After this this ladder, so this is iteration 501 to 1,000. It looks like things are behaving pretty well. So that's essentially to get these kinds of plots, you use the trace plot function in the RSAN package, where you can specify the different parameters that you want to look at, so that's pretty flexible.
Is Stan the one that has the fancy samplers you don't have to do thinning too?
Yeah, so you can do thinning. Yeah, we can talk about that more on Tuesday, but that's the big difference between JAGS and STAN, is that STAN does what's called this no U-turn sampling, and so it relies more on kind of the gradient and bugs and JAGS don't do that. So often, with like a JAGS or a bugs model, you might have to run it for 20,000 or 50,000 iterations, and then as a burn-in, and then maybe another 100,000 where you're doing a bunch of thinning, and it might take a long time. But with STAN, I think it's more often the case. Like, I've never run a model that has required more than 10,000 iterations. I think everything is warm-ups of several thousand and saving several thousand after that with no thinning. So it often is. So as a result, it's often much quicker and more efficient. Overall, it's just more efficient. So. Yeah, that's a great question. All right. Trace plots, we can also look at scatter plots between parameters really quickly with this stan_scat function. And so I think that these are probably most useful if you have situations where maybe you look at the trace plots and it seems like things are not converging. And what I mean by, I think that things would not converge with the trace plot if you saw parameters that were, here things are clearly wandering around. But if you saw cases where the parameter was wandering around and then maybe it was just frozen and it looked like it was not moving from a certain fixed value, or it was looking like it was kind of going through different regimes and not mixing well, then I think you would want to try to figure out why things were not converging. One way to kind of diagnose that are these scatter plots. And so in this case, we'll pass in our fitted object and the different parameters we want to look at. In this case, we see really no correlation between our intercept and our observation variance, which is kind of what we expect. I think if you were fitting a model with like maybe an intercept and a slope, we would expect to see a strong correlation between the posterior estimate of the slope and the intercept. So you'd see this trade-off. So I think for more complex models, this is probably more useful. But this is just one way to kind of look at these correlations. All right, so moving on, more quick plots that we might want to look at are these density plots or histograms. And so the density plots are on the top with what you get with the stan_dens function and the stan_hist functions here. Based on just kind of the eyeball method, it looks like the histograms are not super smooth. So this is kind of indicative that we would want to probably run this more than the 500 iterations that we were running it for, which is not, it's not surprising that convergence here is probably not great given that we only ran it for 500 iterations and saved 500 iterations after that. There's a couple of packages out there too that are useful for kind of making some additional diagnostic plots out there. One is called Bayes plot, and so Bayes plot is just something, again, you get off of CRAN, and one of the more useful functions that I found out of there is just this MCMC areas plot, where you get kind of these are histograms, and it will give you, if you specify the density that you want to kind of show or highlight. In this case, this would be 80% of the area. This plot would ordinarily show you what the different parameters here are on the y-axis, and then the values on the x. In the case of this regression example, it's probably not a great one because the sigma here is on such a different scale from our intercepts. So if you had say random effects, or you had parameters that were on a much fixed effects on a similar scale, this would be one way to kind of show them. And kind of the same information. So this is what you get with MCMC areas. There's a stand plot function again in the rstand package that gives you kind of a one-dimensional version of the same information, where we have our the kind of the interquartile range for the parameters in red, kind of the posterior medians, and then the black lines here represent the 95% credible intervals. So this would be, you see these often in papers where people are just basically plotting these dot plots for a bunch of different parameters on the y-axis and the actual values on the x. Autocorrelation. So autocorrelation is another diagnostic, and if you use bugs and JAGs, you're familiar with this. We've talked about kind of this poor potential mixing of MCMC parameters. In the case of using this as a diagnostic tool, if parameters are well mixed, then it means that every parameter is going to be essentially independent from every other posterior draw is going to be independent from every other one. If we have high autocorrelation, it means that that parameters are going to be pretty similar to each other, and it means that essentially the effective number of parameters that we're drawing is going to be smaller than the actual number that we drew. So if we have, going back to our case here, we have 1,500 parameters. If our autocorrelation, we have 1,500 posterior draws. If our autocorrelation was really high, even at lag 1, say it was like 0.99, that would mean that the effective number of parameters or effective number of draws that we had was not 1,500, but it could be more like, maybe it'd be 50 or smaller. So ideally, we want to see the effective number of parameters that we're drawing be really similar to the number of posterior draws that we have. And one way to ensure that that's the case is that we have autocorrelation at lag 1 is going to be pretty small, which is kind of the case here. Okay, so for more examples on plotting, I think that the examples I showed were just some super simple versions, but there's more examples on kind of the STAN webpage. Then there's two really good introductions here to using Bayes plot and this tidy Bayes functions to look at different ways to display information visually. And there's just like I said before, the number of examples in kind of the STAN manual is growing really quickly, and so I think that there is a ton out there for using this and making some really quick plots with ggplot. Okay, so the tidy Bayes stuff, I think, Eli, did you talk about this last week when we talked about the tidy function with the Mars MLE objects? Okay, we can talk about that next week, I guess. But one of the more recent developments has been this the application of these tidy functions in the Broom library. And so if you're using a regression object or fitting a model with I don't know, GLMM TMB or a lot of different maximum likelihood models out there, you can get these tidy summaries of your model objects pretty easily. In this case, we have a tidy summary, and we can do the same thing with STAN now, where we have tidy summaries of kind of our fitted object here, and it gives us basically an estimate of for each of the parameters. We have a posterior estimate, the standard error, and then the same with the predictions. And going back to the model that we were fitting here, this was the regression model where we only were fitting that constant mean. So we would expect that model prediction would be the same with the same uncertainty for every value of the time series, and that's exactly the case here. So every value, every prediction at time 1 to time 4, all the way to time 100 is going to be exactly the same, which is just a result of the specific model that we fit. Okay, so these tidy summaries are cool, and they're also available in Mars now, but they're great because they can be fed right into ggplot. And so in this case, this is some simple code to basically show kind of the predictions and the error bars for every value of the time series. In this case, as I said before, we're fitting this constant level model or constant intercept model so that our predictions are exactly the same for every value of the time series. If we were fitting a more complicated model with that was like a DLM or something, this estimate would be time varying, and the standard errors would potentially be shrinking or expanding depending on how much information was associated with each data point. Okay, so those are a really simple way to get kind of the basic coefficients out. And then last, I think that when we're using the extract function and thinking about kind of diagnostics and convergence, one of the things that's important is thinking about whether you want to maintain chain order or not. And so what I mean is that if we're fitting estimating 3 different MCMC chains at the same time, by default, we might want to apply the diagnostics to each chain individually, as well as all of the information kind of combined. And so by default, the extract function is going to give you, it's going to basically take the 3 sets of estimates from each MCMC chain and just kind of mash them together without telling you which chain each sample was drawn from or their respective order. So that's important in thinking about calculating autocorrelation, for example. But we could also do the same thing with calculating autocorrelation on each chain for each parameter. So that's probably a better diagnostic tool instead of just calculating autocorrelation on the whole aggregate. And the way to do that is by specifying this, using this permuted argument to specify permuted equals false, and that will give us the chain-specific values for each of those different parameters. Okay, so now moving on to the time series models and using our functions and code for this class. We'll start with just a random walk model, which is should be pretty straightforward and simple at this point. This is the basic equation for the model. We'll take a global temperature data set from this air quality data set, and we'll use our fit stand function to fit a simple random walk model to that data. So the model name here is we're going to change. It used to be a regression on the last example. Here we're just going to change it to random walk or RW. And we have this optional drift parameter. So a drift parameter would let us, if we're fitting a random walk and including a drift parameter, it would basically be a non-stationary process, right? It would have some kind of trend that would be increasing or decreasing through time. But in this case, we're going to assume that the drift is essentially 0. So we'll turn that off by saying estimate drift equals false. And everything else will be the same as before. So we'll have 3 MCMC chains. The iterations of the burn-in will both be 500. And then so things will fit really quickly. One additional diagnostic check to look at is what's called R hat. And so if you've used bugs and jags before, this is also, it should be familiar because it's a similar output from those software tools. But R hat here is just kind of a diagnostic tool. We want to see small values that are less than 1.05 or whatever threshold you specify. It kind of changes depending on who you ask, but some people might be more conservative and say 1.01 or smaller. If you have values that are 1.2 or 1.3, that's much more problematic. So in this case, what we'll do is just apply the summary function to our random walk, the object that we just fit on the last slide, specify which parameters we want to calculate this for. In this case, we want to look at the parameter sigma, our observation error, and I think that this shouldn't be cut off here, but the R hat here is about 0.999, so it's about 1, which indicates things are converged. It's sometimes problematic if this thing is less than 1, and so in this case, it's probably just a symptom of the fact that we ran this for such a short amount of samples. So I think if we ran this longer, things will probably be just over 1 and also less than 1.05. Okay, so moving on, state-based models. So the equations here are just, we have a kind of a univariate state-space model with just an AR term would have this would be our latent state, the equation of the latent state. This phi parameter just represents the degree of autocorrelation. In this case, it would be bounded between 0 and 1, as Mark and Eli talked about a couple weeks ago. Our process errors here are assumed to be normal with some standard deviation q, and I'm just using a little q here for standard deviation to be consistent with kind of the Mars notation. And then on top of that, we layer this observation equation. So we have our data, the y sub t is normally distributed with around some mean, the x sub t, and again, we have some standard deviation, the little r. So that should all be kind of a review. One thing we might want to do is take our temperature data set and then just compare how two models differ with respect to basically turning this parameter on or off. So how much support is there for including that phi parameter? So there's two different models that we can fit using our kind of fit stand function. Again, we'll use the exact same temperature data as before. We'll turn off drift in both cases. In the first case, we'll estimate what that phi is as a free parameter. So that model is just going to be state space underscore AR for autoregressive. And then we'll also fit a simpler model where we're fitting this argument will be SS underscore RW, where it'll be a state space random walk model where that phi will be fixed to 1. And so in this case, we're essentially looking at the differences between turning that thing on and off. Let's see here. Okay, so estimates from these are first the estimates from the AR1 state space model where we estimate phi. The blue points here represent data, and the shaded region represents the credible intervals or uncertainty, and I guess the posterior mean would be right in the middle of those. So these are the estimates from the AR1 model. These are the estimates from the random walk model where that AR parameter is fixed to 1. And so flipping back and forth between these really quickly, essentially they're exactly the same, right? So we could also, another way to plot them is just to show them on top of each other. And you can see that in some cases, there's just a very, very slight difference in their uncertainty bands, but essentially they're giving us the exact same mean estimate and the exact same uncertainties. And so thinking about this, we could think about why this is or how we might diagnose this. And I think it's pretty intuitive, because if we have these two models where one where we're estimating this phi and one where we're not, we're fixing it to 1. If the posterior estimate of phi is very close to 1, we're going to basically get the same behavior. And so when we use the stand underscore dense function to look at the density of what phi actually looks like, the posterior is basically slamming into 1, which shows us that we're essentially getting the exact same behavior from the two models, because that phi parameter is really close to the value that we're also fixing it at in the second model. Okay, so then you can do all kinds of things. You could calculate, this is a temperature model. We could calculate probabilities of exceeding some threshold, because every value or every prediction from this model is going to be a valid density or probability distribution. So we could ask the question, for example, what's the probability of exceeding a temperature of 90 degrees? And so this would be some simple code to do that, and the answer here is a little over 7%. So it's you can do all kinds of summaries like that too. Moving on to the multivariate cases, Mark talked about DFA. I wanted to just show a quick, simple example or how to set this up using the stand code for this class. In the Mars package, it's a bit confusing, but I think that there's basically 3 different versions of the Lake Washington plankton data set. And so in this case, we'll just use this one that's been kind of transformed already and z-scored. So just a reminder, all the zeros were replaced with NAs. Then the data were z-scored. And here we'll only use data from 1980 to 1989 just for simplicity. We'll also restrict the analysis to just these five groups here, which are in the phytoplankton array. So the data basically look like this, which should be familiar. All of these are basically stationary with respect to maybe not the unicellular time series on the bottom left, but everything else is pretty level. So the second function that we have put together is fit underscore DFA. And so in this case, we were using the fit underscore stand function before, but this will basically fit a DFA model in a Bayesian setting. Our data inputs here are just the transposed data, and then we specify the number of trends. We can fit models up to basically any number of trends you want. And then I think just a reminder is we talked about this rotation or the need to rotate loadings and trends when you use DFA. In a Bayesian setting, we need to do the exact same thing. And the main justification is this issue that we keep running into with identifiability. And so I think that one of the best examples that I think about when I think about identifiability in DFA is that if we have 5 time series and we fit a DFA using Mars, and then we reorder the time series so that maybe we shuffle just the first and the second time series, the order of those, and then refit the model, we're going to get different answers, and we're going to get different estimates of the trends, different estimates of the loadings. But the solution to that is to just do this transformation. And so when we do use the Varimax rotation or some of these other methods, like we did in Mars, that issue goes away, and the results are insensitive to the ordering of the time series. And so, so we have a function here too that we call rotate underscore trends to basically do the rotation for you using the Varimax rotation. These are just the attributes of those objects, which I don't need to get into, but basically these are just different summaries of the rotated trends and loadings. Because we're doing this in a Bayesian setting, we can get the mean and the mean of those, which is really what we care about. But you can also imagine doing that for every single MCMC draw. So if we have 1,500 different posterior samples, there's essentially 1,500 different realizations of that Z matrix and 1,500 different realizations of the trends, and we would have to rotate each of those individually. Okay, so by default, the variance structure in our fit DFA function is just diagonal and equal, but like Mars, we include a lot of other different variance structures that you can play with, and you can choose a lot of different ones using this additional argument, which we don't need to get into until we actually deal with this in lab. Uncertainty intervals on the states, and so I think we've talked a lot about, with DFA, we've presented the estimates of the trends. I think it's also probably just useful to also show uncertainty estimates around those trends. And so just as an example, with the Harbor Seal data set, this is time series of abundance this is just the inland stock of Washington. And so we are just going to fit a DFA, assuming a single trend for this population. I think it's important to note that for 3 of these time series, we have data for going back to basically year 5, and then about year 15 or so, we start getting time series for the last 2 populations. So this is how we basically use our fit DFA function to get the extracted trend for the Harbor Seal data set. This middle block of code is just kind of an ugly way to create a data frame with the predictions, and then our low and kind of low and high values for this for these error bars, and then we just fit a geom ribbon plot showing that uncertainty interval. And I think what's interesting is that as we said before, we basically had no data up until year 6, and so you can see the uncertainty estimates are kind of ballooned here because there's little data, and then once our data starts to get collected, we see greater precision. And then if you really wanted to zoom in on this, there's when you get gaps in the data, you would expect to see uncertainty estimates increase a little bit. So in the case of the harvest yield data, there aren't any huge gaps where the data are collected and then missing for 10-year stretches, for example. But if that were the case, you would see the uncertainty estimates would really start ballooning again. Okay, so then the last function, I think or last set of models that we have to fit here are just the Bayesian equivalents of the DLMs that we'll talk about in the lab today using Mars. And so we have 3 different flavors of fitting DLMs. These are just 3 different examples to Mark's logit transform survival of salmon from the Columbia River. And so in this case, we're going to be passing in the same data, and we can fit a DLM with just a autoregressive process in the intercept using the DLM intercept as the model name. So this is kind of what that plot and the estimates look like. So we have this random walk. This is kind of what the estimate looks like through time with the geom ribbon plot again. So that's just kind of the intercept model. We can do the same thing using a slope model. In this case, our slope model, for that to actually work and make sense, we have to pass in a covariate. And so I took one of Mark's other examples and used I think the equal upwelling is the predictor, the X. We're going to change the model name from DLM intercept to DLM slope. And in this case, I think what this mostly illustrates is that the model has a really hard time converging. In most cases, the estimates are close to 0, which is kind of what we expect. But then there's a few blips here where things really blow up and the uncertainty really blows up, which is just indicative of there's something that's not consistent between kind of our predictions and the actual data that we observe. And then finally, we have kind of the last example of fitting a DLM with this SAN code is to fit kind of time-varying models with respect to both the intercept and the slope. And so to do this, we would just specify, instead of fitting the model name as being DLM-slope or DLM-intercept, we would just set model name to DLM, and that would include potentially both. So that's something we can explore more next week. But just to kind of summarize on this before we transition to lab, the Bayesian implementation of these models is very flexible. It can basically do everything that Mars can do, and then go beyond that with non-normal data, nonlinear parameters or nonlinear relationships, hierarchical parameters. It's very widely used by people in SAFs and Quirm, etc. And if you want to adopt this for your class projects or beyond the scope of this class, certainly come to us with any kind of questions or help, etc. Eli.
Can you talk a little bit about the options in the STAN package for the class for non-normal data, because you have that incorporated in some of the functions?
Yeah, I think we'll talk about that more on Tuesday when we're kind of writing our own. But yeah, that's good. Yeah.
They can't pass in different distributions. Is that possible?
We have to specify the distributions ourselves. Yeah. For some of these, I can talk about that more next week, and I think in the lab next week we'll get into that more. But yeah, that's good.
Is there an instance where it'd be better just to use Mars instead of the Bayesian implementation?
Yes,
well, it depends a lot what your objectives are. Mm-hmm. Like if you have non-normal errors, if you have like 0 inflated data, then you're going to want to incorporate that in your model. And there are ways you can do that with a Kalman filter. I'm pausing there because in my experience, when I do it, I'm like, oh no, I'm just going to write it in Bayesian framework. It's just much easier to think about. So that's one context. However, if you can write your model down in a Mars equation and you feel comfortable in the assumptions about normality of errors, then the Mars model is going to allow you to really quickly fit that model and look at its properties. You may well still want to write that in a Bayesian framework because you're trying to get something like, what is the probability that this parameter is in this range? So that is a Bayesian question. So yeah, it depends what your objective is, and it depends whether or not you can accept the assumptions underlying the Mars model. One other thing I will say, and Eric, maybe you can comment on this, is that my sense is that sometimes setting the priors in your multivariate models is nuanced and not so easy. And with the Mars model, you don't have to worry about the prior.
Yeah, that's a really good point.
Variance covariance matrices.
Yeah, putting priors on things like the variance covariance matrices is really hard. And that's still a rapidly evolving field. I feel like so that's a multivariate prior. I feel like thinking about these interaction matrices, and we'll talk about that more in the class later, but those are things that also are, they're not only, so it's multivariate, but then there's all these weird constraints on them. So there's, there's constraints on them being between 0 and 1 or -1 and 1, depending on the elements. So I think any of these parameters that have weird constraints, it's really hard to put priors on them. So yeah, I think like what Eli said, if you can write down the model in kind of this framework, and and it's reasonable to assume your data are normal, especially if you have a large data set, then I think that using maximum likelihood estimates are probably a much easier way to go. And you get very similar answers in most cases.
Another situation that you'll run into where people often will use a Bayesian model is where you are combining different types of data, and very different, right? So it's not like you can treat all your data as being time series data that are autocorrelated. So basically, fit the assumptions of the Mars model. Maybe you have some time series data, but you also have the single time surveys that are going to give you information about the population density. You have some other type of data that is one survey, and that's going to give you an estimate of the ratio of two time series within your data. So you say the two time series of different age classes, right? You have some age or size distribution samples, beginning and at the end. Right? That's not time series data, but that has important information about the relative value of these two time series that you're trying to analyze. In a Bayesian framework, it's much easier, much easier to combine two models where you have a likelihood. You have a model, right? So you have a likelihood of each type of data, and you want to use all that information together to help make an inference about what these two underlying states of the density of these two ages. So
yeah, I mean, I guess like another good example. I mean, another like real world example would be things like Leslie matrices. I don't know if people have ever used those for doing like population projections. So a Leslie matrix is like if you have like age structured data or stage structured data where you have say you have 3 stages, the elements of that matrix represent how the population at time t transitions to the time set to population time t plus 1. And so you have some survival rates that are kind of on the off diagonal of that matrix, and those survival rates have to be constrained between 0 and 1. And then you have some fecundity elements on the top of that matrix, and those are just constrained to be positive. So you have these weird constraints to begin with. you have a lot of the elements of that matrix that are probably zeros. And then the multiplication is not happening in log space, which is what Mars is doing, but the multiplication is happening in normal space. And so we've tried in the past to get kind of that type of model into this framework, but it's not exactly the same. And so I think because of that, if you have a model like that you want to fit, I think it's probably much easier to do it in a Bayesian setting, or to do it using maximum likelihood tools that are not Mars. And so I think in previous iterations of the class, people have used like AD Model Builder or template TMB is kind of the newer tool. And so, for example, somebody took kind of the DFA model and wrote their own implementation in TMB, and it's as fast as Mars, but it's just offers a little bit more flexibility in terms of the distributions you can put in and constraints and things like that. So that's another kind of workaround, I guess.
You should also be aware of the danger of kind of cooking your own statistical model, say the Bayesian framework, is that it is easy to build models that are not properly constrained. They have multiple solutions. And you will see that in your autocorrelation chains, that it never seems to converge. It kind of wanders here, maybe wanders over there. Worse yet, it has two solutions, and if you don't tune things right, maybe it's stuck on one solution and you never get it to jump over to the other solution. Working within a set framework, and this is, it could be like Mars, that's a framework, but it also could be a Bayesian model that is well established in the literature, and these issues about identifiability of the parameters are they're known and they're discussed. So if you're working with a known framework, you can avoid those issues. Or if there are issues, somebody has kind of worked out how to address them. Once you start like getting up on the whiteboard and let's have this model, we're going to have this nonlinearity, and okay, wait, let's have this other data stream here with these parameters. It's really easy to create something where you have two parameters that explain the same statistical patterns in your data. And you need to work with somebody who has experience in evaluating those problems, like looking at the likelihood surface. You're looking for ridges, you're looking for certain behavior and how the MCMC chains are behaving. And somebody with experience would be like, yeah, I've seen that before.
All right, so should I pull up the lab here?
Yes.
Did you guys do a separate recording for the lab, or?
No, I'll get up and talk about that.
Okay. Do you want me to just leave the recording running then? Here?
Leave that running, yes.
Okay. Let's pull this up for you then.
Go to the computer labs. DLMs, yeah. Open the HTML. Okay. If you have not already, make sure to watch the lecture by Mark on dynamic linear models. The chapter in the lab book will does cover all the material that is in the lecture, but it adds more examples for you to go through, and it gives you all the code. So when you go here, you can go ahead and
Oh, I guess that did that just automatically download that? Yours is behaving differently. Yeah. So you'll be able to download this DLM markdown file and work through the code in this lab. Okay, so how many of you watched the lecture? 1, 2, 3, kind of. How many kind of watched it? Yeah, okay. Huh? Okay. Okay. I'm going to go over what DLMs are then for the benefit of everyone who did not watch it and those of you who just kind of watched it while also watching something else at the same time. Okay, so a dynamic linear model is like a linear regression. So here's a linear regression. We have our response variable, and then we have a predictor variable. In this case, I've just got one predictor variable, so it's really simple linear regression. I've got an intercept, and I have the slope, the effect of the covariate. Okay, really simple linear regression. We can then write that in matrix form, like this, where we've got our parameters here, and then we have our predictor variables here. We have one for the intercept and one column for our predictor variable. Oops. So what's different in a dynamic linear model is that instead of having these fixed for the whole time, we instead think of these as time varying. So they can change and evolve over time. And specifically, what we assume is that the theta here are those, is that matrix of alpha and the beta. We're going to assume that it evolves via a random walk. And by specifying that time dependency, that's what allows us to allow those variates to evolve over time. So, right, if we had if we like tried to estimate a different intercept at each time point, and then a different slope at each time point, we would be trying to estimate twice as many parameters as we have data points. That obviously is not going to work. If we specify that the parameters evolve over time like this, then let's say the GT is just a fixed number here. All we're estimating is a variance term. So it's one parameter. So let's see this. Okay, so up here is how you will see a dynamic linear model written in the DLM literature. It's going to look like this. You got your response variable, and they're going to write these covariates as the transpose of a matrix, and then you have your theta are your parameters, and then you have the equation for the theta here, which this is a random walk. You see that time dependency there. Well, if you look at that, you'll see that's just a Mars model. So just see one-to-one here. This Z is that. This X is that. And all we're doing is changing the notation that we're using. One thing that's different than many Mars models is that the way that that these multivariate autoregressive models, how they incorporate covariates. And we're gonna see this in a couple weeks. So like if you're modeling, these population trends like we've been doing last week, and say you wanted to try to correlate that with some covariate, you're going to incorporate that. This is the X model, but let's say you wanted to incorporate the covariate in the observation error. You would do that by adding this covariate here in this column vector over here. But it's really different with dynamic linear models in that your covariates appear over in this matrix in front of your X. Usually, like say in the DFA model, where we have this Z matrix, it's, remember this is our loadings. So these are parameters we're estimating. So typically, most of the examples we're going to show you in the class, these matrices that the matrix that appears in front of the X is a parameter we're estimating. But in the DLM, it's our covariates. And the reason is this right here, the way that the dynamic linear model is written, where you have your parameters you're estimating here, because these things are going to be evolving over time, and then that means you put your covariates in this matrix that's in front of the X. There's your X. There's your matrix in front for the covariates. So let's see some simple examples here. This is about the most simple example, and it's called a stochastic level model. And in this model, we have a linear regression where we have no covariates. All we have is an intercept. So if you were fitting this in LN, it would just be putting a straight horizontal line through your data. But now we're going to say, well, no, we're going to let that level evolve, and we're going to say that that level is a simple random walk without drift. So that there is what's called the stochastic level model. In the Mars notation, looks like that. So that alpha there is the X, and then the X is a random walk. If you wanted to fit this with the Mars model, all you need to do is look at that equation up there and then tell Mars the structure of all the parameter matrices. So you look, there's a B in front of the X right there. It's a 1, so you'd say it's identity, or you could say matrix 1. The U doesn't appear, so it's 0. The Q is something we're estimating. So we tell it, we're going to estimate that. The Z up there is just a 1. We can say identity, or we could say matrix 1. A, I put an A here. It's not up there. Okay. I added something. It's all right. It'll still fit. And then the V up there has a variance, and we specify that. So all of this is that model right there, and then we can just pass that model list in and fit. So then you get that. You saw examples of this in when you read the chapter on the univariate state space models. I used an example of the stochastic level model there too. Let's see. Okay, I'm good. There's one more. Oh wait, let's do stochastic regression. Right. Okay. So now we'll go into an example you haven't seen before. So now we have we're going to add a covariate. So there's our covariate. And what we're going to say is that the intercept is going to vary through time, and the slope is going to vary through time. So both of those are going to vary. You need to write that in matrix form. So here you go. There are two parameters. They vary through time. Multiply that by your covariates. And here is the equation for our intercept and slope. It's a random walk. There it is, written in Mars notation. Once we have it in this notation, we can fit it with Mars. Did I do that? No, I didn't do that for this example. But you're going to see that with this section, which you should work through, which is an analysis of salmon survival. And it's going to use exactly that model that I just showed, where you're going to have the intercept and the effect of this upwelling index. That's what your F is. It's going to vary with time. So one kind of interesting thing that you can do is that now that you've got this model of your parameters, you can specify what the variance covariance matrix is. And you could specify that these two parameters are not independent. So you could, in this case, I've said they're independent. So that the way that the intercept is fluctuating through time is independent from the way the effect of the upwelling is varying through time. Made those independent here by putting zeros here. But you could change that and say that these are correlated. That might make sense if, you know, if you're looking at how the beta, say you had two covariates and you wanted to allow that the effect of those two covariates was changing in a similar way over time. You could allow that now with this structure. Yeah?
Would you fit it, or would you give it a fixed? Or is it just dependent?
You could do either. So if you'd have to specify both what the variance and what the covariance was. And there could be situations where you may have a lot of prior knowledge about how that might be varying from other analyses that you've done, and so you specify ahead what these values are, and then your objective is to estimate what that intercept and what that beta is over time. So you want those state estimates. But in other situations, you might want to estimate this, and you might be interested in determining if that covariance is different from zero. So is there evidence that these are these changes in the effect of your two indices? I don't know, one's upwelling and one's sea surface temperature. Is there evidence that they're kind of changing together or not? Okay. This section will show you how to incorporate, or one way to incorporate a seasonal effect in a dynamic linear model. So this shows you how to incorporate a quarterly effect. And this is kind of an interesting example because let's say, well, I'll walk you through it. I'll kind of show you how it's interesting. Let's say that the seasonal effect, the quarterly effect, is not changing over time. So you're just treating the quarterly effect like this. The intercept is changing. The slope, the effect of x, is changing over time. But the quarter is just a fixed level, constant, that depends on whatever quarter you're in. So if you're quarter 1, it's going to be that. Quarter 2, it's that. Quarter 3, it's that. Quarter 4, it's like that. So we can write that in matrix form. Here we go with our quarter. And so now we have a third column for quarter. But now we have to keep track of which of our gammas to add there. So we have 4 of them. So actually, what this matrix here looks like is something like this, where if we're in quarter 1, it needs to look like this, and we would need to pull off that gamma. But if we're in quarter 2, it looks like this, and we're going to pull off this gamma. So you can imagine how you would set this model up, and imagine it's going to get cumbersome really fast, because we're going to have this matrix vary through time. It's already varying through time because this is varying, but we're going to have to vary the location of our zeros and ones here depending on the quarter, which we can do. It's just a little bit cumbersome. Got to make sure we don't like accidentally, have it look like this when it's quarter 1. We could do that, and we might need to do that if, say, we wanted to model these gammas as being time varying, which we could. We could say that we want to estimate if the effect of quarter 1 has been changing. So we wanted to estimate are the quarter 1s getting overall hotter over time. That would be a completely reasonable thing to want to look into. And if we did that, we'd have to set things up like this, and we'd have a autoregressive model, a random walk model for these. But let's say we didn't want to do that. Let's say we just want to have a fixed effect of quarter. Well, then we can do things very differently. What we could do is we could keep this the same, and we could vary this. So in quarter 1, we have it look like this, but in quarter 2, we shift this down, and we move that up. So now this location is staying the same, and we've rotated this. So we could do that. And you might think, oh my goodness, how could that possibly help you? Now you've switched, like, trying to keep track of this to keeping track of this and having these like rotating. That seems horrible. Well, actually, it does seem that way. But the neat thing is that you could use a permutation matrix that will do this rotation for you. And let's see here. This trick of using a rotation matrix, or a permutation matrix, not a rotation matrix, a permutation matrix, is a trick that comes up in a lot of different situations. So let's say, okay, so this is quarter 1. We want this column vector to look like this, right? And in quarter 2, we want it to look like that. Well, if you look, if we set up this matrix that goes in front of the x, so this is xt plus 1 is g times xt plus the process errors. So these are not changing, so we have to make that 0. We can do that. These here are the ones that are changing. They have their process errors. And now look, we put these zeros and ones here, And you can see that now the third row becomes Y2. The fourth row is going to become Y3. And the the fifth becomes Y4, and then the bottom one becomes Y1. So it's rotated it for us. At t plus 2, it's going to do the next rotation. So that way, we don't have to have this matrix just keep changing. We're just going to keep it like that the whole time, and then we add that G matrix in front of our X's. And we just specify this, and we just pass this in our model specification. Okay, right, so you should go, we're going to pause in just a moment. You should go through this, see how to fit these. There's a section that talks about forecasting. And forecasting your DLM means that, so let's take the example of you're fitting a DLM where you have a covariate, and you want to forecast the, let's go back to the salmon survival example. So you have a model for salmon survival, and you're modeling that as a function of upwelling. And you would like to make a forecast of what the salmon survival is going to be next year. And you're going to use the upwelling index for next year to help you generate that forecast. So you're in this year. You have the upwelling index this year, and you want to use the data from last year plus the upwelling index this year to make a forecast for what the survival is this year. So what you need to do is you need to get an estimate of the regression parameters. So that's that alpha, the intercept, and the slope. Remember, those are changing over time. So you can't just use the value last year. You're going to use that process model, that random walk, to make a forecast of what the intercept and the slope should be this year, based on what you knew last year. You got to get that, and then you can use that along with the upwelling index for this year to make a prediction about salmon survival. So the tricky part with that is figuring out, okay, so here's the math here. So this is your estimate of salmon survival this year, and it uses your estimate of the parameters this year along with the upwelling this year. So this T is this year. This is the estimate of those regression parameters for this year, conditioned on the information up to last year. So that's pretty simple there, right? We could just do that math. So that right there would give us the expected value of salmon survival this year. And it's just that right there. The problem with that is, I mean, that's great, but we also want to know how uncertain that is. And so we need to get the variance of that. And that part is a little trickier. Takes a little bit of math that's discussed there. But it's pretty easy. And then once you have that, you'll go through, you can do things like this, where you can make, this is a series of forecasts, where you're forecasting, each case you're forecasting the next year. So let's say here, we're going to forecast this year based on the data up to here. And then you can make your predictions of how uncertain you are about that forecast. Okay, 307, let's go ahead and pause for 10 minutes, and then you guys can work on it, or if you have other questions, we'll just be sitting here so we can, yeah, help you out. All right.
Yeah.
Sorry.
If, Mark, if you want to talk with us about your project.
Yeah. Now's a good time. Or,
Today.
okay.
Not right at this exact moment.
Yeah, okay, let me look at this a little bit. Maybe at 3:30 or something.
totally wonders, like.
You're the thing still recording.
Yeah, I'm gonna stop.